Welcome back. Today we're going to take a look at the partial derivative definition. And when working with problems of different variables, it becomes important to understand how a value of a function will be affected by the change in only one of the independent variables. Think in an experiment like in science, we might only want to change one variable at a time. For example, you might be trying to study different medications and how they affect the patient. So how does it affect one patient if you only increase the dosage? Or what about if you extend the amount of time between dosages? So we only want to change one variable at a time. We will be using a similar idea to calculate the rate of change of a function to one of its independent variables. This process is called partial differentiation or partial derivatives. These are the definitions for the partial derivatives of a function f with respect to both x and y. Mathematically, we calculate these partials by differentiating with respect to x if we treat x as a variable and all other variables as constants. In other words, for the first one, this is considered the derivative right here. This first one, we consider that the derivative of f of the function f of x, y in terms of only x. In other words, we treat y like it's a constant. So anything else that's not an x gets treated like a constant. And of course, this will be the derivative of our function in terms of only y, where we treat all other variables like x as a constant. So again, this is just a notation that we tend to use for fx, fy, f sub x, f sub y. Another notation we use, we can talk about what's called the partial derivative. In order to differentiate, though, the difference between the derivative and partial derivatives, we use the Greek symbol delta. Now this is again the Greek letter delta, but in this case it's the lowercase delta. Again, for change. Remember this? Delta y over delta x. This is the capital delta in Greek, where this is the lowercase delta in Greek. And again, it's talking about the change. And again, this is the notation that we more commonly use because, again, it's that Leibniz notation, which has many more applications for us. So what this is telling us, so if we have the first one, this is the partial derivative of the function x, partial derivative with respect to x. And this is also saying the partial derivative of our function with respect to x. And that's what these both mean, that these are the partial derivatives in terms of x. In other words, we are looking for the partial derivative with respect to x. And we can do the partial of f with respect to y, or f sub y, if we're looking for the partial derivatives with respect to y. So let's look at an example. Let f of xy, so this is a function, equal x squared plus e to the y. We want to find the partial derivatives. In other words, we want to find the partial derivative with respect to x and the partial derivative with respect to y. These are called the first partial derivatives. And yes, we have second partial derivatives and so on and so forth. We'll talk about those in another video. So the first thing we're going to do is we want to find the partial with respect to x. So f sub x. Now this is now a derivative. Notice we're not using a prime anymore. We use f sub x of xy. Or you could also use the partial of f with respect to x. Mine always tends to look like a 2. Sorry about that. And if I take that derivative, what we're going to do is we're going to take the derivative of anything with an x. So what is the derivative of x squared? Of course, that's 2x. What about the e to the y? Well, that e to the y is not in terms of x. Is not in terms of x. Therefore, we treat like a constant. And therefore, what's the derivative of any constant? 0. So we can go 2x plus 0. Therefore, our derivative, the partial of f with respect to x. Now notice we call it a partial derivative because we're only taking the derivative with respect to x. So that's what we call this a partial derivative. We're not taking a derivative with respect to y. We'll talk about that later on. We can take them both. So that becomes 2x. If I want to find the partial derivative with respect to y, it's f sub y of xy. Remember, we're not using primes right now. We're using f sub y. And taking the derivative, this is the same notation as if I did the partial of the function with respect to x. Oops, sorry, y in this case. There we go. And its derivative, well, in this case, x squared is a constant because there's an x, there's no y there, so that becomes 0, plus e to the y. Well, e to the y is its own derivative. That's just e to the y. Therefore, our partial derivative with respect to y is just e to the y. And there's our answer. Now, later, we're going to write these as matrices. This is called, and some of you might have seen this before, this is called a Jacobian matrix. If you're taking modern physics or just really enjoyed math that you studied ahead, we call it a Jacobian matrix. And we use these all the time. We use these in statistics, engineering, in physics. In physics, we actually call these tensors. Okay, so there's a lot of relationship between the partial derivatives and how we use them in science, math, and beyond. All right, so let's take a look at another quick example real fast. So here we have the function f of xy equals x e to the x squared y. We want to find the first partials. That's what this is looking at right here. We're looking to find the first partials, the derivative with respect to x and the derivative with respect to y at the point 1 natural log of 2. So right here, these are our partials, partial derivatives. Right. So if I want to find the derivative with respect to x, now if you want to use the partial derivative, the little partial symbol, the delta symbol, that's okay too. Now if I want to find the partial with respect to x, be careful. Oh no, I got to use product rule. So let's see if we know how to do product rule. It is the first times the derivative of the second plus the second times the derivative of the first. So the first is x. The derivative of e to the x squared y becomes e to the x squared y times chain rule. The derivative, be careful, y is a constant. That just becomes 2xy. Plus the second, e to the x squared y, times the derivative of x, which is just 1. Ugh. So there's our first one. That's pretty nasty. Okay? They do want me to find the slope at 1 natural log of 2. So I'm going to go ahead and evaluate that. 1 natural log of 2. And if we plug this in, we're going to get, well, that's x is just 1. This becomes e to the natural log of 2 times 2 times natural log of 2 plus e, again x is just 1, to the natural log of 2. And if we simplify this, that just becomes e to the natural log of 2 is 2. So we're going to get 4 natural log of 2 plus 2. So what does this mean for us? Well, let's take a look at our graph. Here we have this line right here in the x direction right here. So what does this tell us? Well, this is saying this is the slope of the function in the x direction. So here's this red curve right here represents our function, x e to the x squared y. What this is telling us is that this is in the same direction as x, this is our slope, f of x, xy. At that point, wherever that point is, this is giving us our slope at that point in the x direction. So this is telling us how our rate of change in the x direction is changing. Well, sorry, yeah, it's just telling us how our x position is changing at that point. Finding the y, fy. Taking the derivative, I don't have to use product rule here because the only y is up here. X is just like a constant. So this is just going to become x e to the x squared y times, well, the derivative of the inside, be careful, x squared is a constant, so x squared times y just becomes x squared. So we can simplify that by making this x cubed e to the x squared y, and then plugging in your point, 1 natural log of 2, we're going to get 1e to the natural log of 2, which is just 2. So again, what does this tell us? This is the slope of our function in the y direction. In other words, if we go here, there's my y-axis. If we go in the y direction, this is the slope of that tangent line in the y direction right there, not drawn to scale. So, and that's what this is kind of telling us. The partial of f with respect to x is the slope in the x direction. The partial of x with respect to y is the slope in the y direction. All right, go to part 2. We'll continue on. I'll see you then.